I'll share through my tablet. So wait a minute, I'm joining with another device. Feel free to stop me anywhere, ask your doubts. You can directly message me. I'll keep reading the chat anytime. Uh, yeah, and let's keep this as much as interactive as possible. And yeah, invariably, I would do some mistakes, and please point it out. And because even I am learning with you all, and I might not know everything. So, yeah, please feel free to ask doubts and correct me whenever possible. So, having said that, mm, yeah. So, I'll first initially start with just some fundamentals, and the hope is that you know already and have done your homework and you're familiar with all of these. But yeah, just to give you an overview. Uh, so we are currently the review is on Bayesian machine learning, and this is a very much like built on the fundamentals of probability. So I'll give you some few key concepts, but yeah, let me just go ahead and ask you some one of the basic questions. So can anyone here define like a random variable? And yeah, so I'll keep asking you such questions. So the hope is like to keep it interactive and to ensure that you are along the right track with me. So you can like answer it in the chat or just unmute yourself and say it out loud. And yeah, please don't feel shy or anything because yeah, this is not so formal. So yeah, just learning. So uh, yeah, please anyone define a random variable.
Um, Random variable can be like roughly it can be defined as a number or a function that maps an event to its probability.
Yeah,
So it tells you that how certain or uncertain a particular event is likely to occur or not.
yeah. So like this is one of the fundamental questions that like people ask in interviews, and yeah, many people fail to give a proper answer, but like this is correct. So uh, yeah, like a vague definition would be a random variable is a variable that takes random values, and like that's correct, but that doesn't give you an intuition of like what exactly does a random variable do. So like in probability, so now yeah, so random variable is just something that maps like let's say yeah, I would relatively I would like for a few times give this example of coin toss of heads and tails. So assigning like heads is some event in the sample space, and then assigning it to any measurable number. So any state space, like in formal terms, but we can for a univariate distribution we can just assume that to be a real number. Yeah, uh, that's for uniform distribution. For univariate distributions, and for multivariate distribution, any real number, like any n dimension vector. So like mapping heads to zero. So this is some event in sample space, and random variable takes this and like maps it to a number. So yeah, assuming like since it's a univariate distribution, so now this would always belong in just one variable. So yeah, so that's basically what random variable is. And so, and now uh, obviously now this random variable can take many values like to the number it maps to. So if it can be like it can be some discrete set of numbers, like basically any countable set, or it can be like, uh, just any number in the real line, basically a continuous set. So this would be a categorical distribution, more like discrete distribution, and this would be uh, like the distribution on x would be discrete, and we call x as a discrete random variable. And similarly, here x takes continuous value, so it would be continuous random variable, and distribution on it would be a continuous distribution. Now, many a times I would generally like skip writing it, so people just think that this indicates probability distribution of just x, or probability mass function of x. But whenever you like you need to calculate certain value, you'd also have to mention that like what value does it take. Sometimes people just generally skip this. Whenever I'll write, I'll make sure that capital letter is the random variable, whereas smaller case letter is the value that that random variable is taking that we are trying to calculate. Uh, so sometimes I might skip writing this, but whenever if I write some equation as some function of x, then just know that this x is not the random variable itself, but it is the value that uh, random variable x can take. There is always a distinction between the two, which is not always made clear, but in your head, like just ensure that it's clear. Okay, so this is all I wanted to talk about random variables, and then uh, I would just go over a few notions in probability, which would be very helpful in the coming lectures. So, starting with first, obviously, you would know what independence independence of two random variable indicates. Uh, in simpler terms, probability of x, y. Yeah, and since we'll be dealing with this joint probability so much, probability of x, y is nothing but probability of x and probability of random variable y. Uh, yeah, so basically it would be which would be a function of x comma y. But yeah, so since we are dealing with joint probability, this and or maybe if you want to call it intersect, uh, yeah, if you want to call it intersection and all of that is skipped, and we just write comma instead of that, but it's nothing but it's just joint probability, taking all the variables together and asking what probability that would take. So, but yeah, so the independence comes in the fact that if this function of x and y can be simply decomposed to function of x, function of y, where p of x is equals to x is function of x. So yeah, so but what this like intuitively it's quite easy to grasp. Okay, like if I give you two extremely random events like tossing a coin and say probability of you not getting COVID positive. So these are two extremely random events, and here like you can see, okay, these are two random independent events because they are not related to each other. So finding independence is like easy when you know the story behind it, but in reality it might be an issue. So Hello. Yeah,
Yeah, I think you were muted for some time. Were you saying continuously?
yeah.
Okay, okay.
So when was I muted?
Just
I'm
now,
not
like
sure.
x1 plus x2,
Yeah,
that
x1 plus x2.
kind of like element wise operations.
Yeah. So you heard everything till here, right?
Yeah, yeah,
Yeah.
yeah.
Yeah. So I was just saying that sometimes intuitively it's very easy for us to get independence when we know the story behind how those variables like yeah. So what does x like if x1 is the probability of heads or tails, and then x2 is like probability of say Arsenal winning the football match. So these are two like completely random events, and then random events, but at the same time they are independent because there is no causal reasoning assigned to each of them. So it's easy for us to see that okay, there is independence in that, but in reality, in the problems that we face, like to assume independence between two variables and to decide okay, these two random variables are independent is an extremely difficult task. So let's say now this is this is x1 xor x2 is equals to y. So yes, it's basically x1 x2 y 0 0 1 1 0 1 0 1 1 1 0 0. Yeah. So now can you tell me if x1 is independent of y and x2 is independent of y, x1 is independent of x2, x1 is independent of x2 is independent of y. Yeah. So can anyone like just mention it in the chat and like in the order whether which variables of these are independent? So this is the function that we are talking about. X1 XOR x2 gives y. How and this is like this is the common symbol to indicate whether the two random variables are independent or not. So please, anyone, and even if you can't, then just like tell me how would you even go about finding okay whether these these two random given this function whether these two random variables are dependent independent. And this is some basic stuff that you should know. So and yeah, please don't shy away from answering or anything because this is supposed to be completely informal. So just think of me as some like friend and colleague of yours who is just presenting you with something which might be faulty at sometimes.
Like x1 and x2 both, in a way, if we consider that, that should be kind of independent, I feel. Like the output y, like what it takes depends on like basically what x1 and x2 values like are, but x1 and x2 values like in
Okay,
both are independent in a way, like it does maybe.
so this is independent. That's correct. X1 and X2. What about X1 and Y? X,
Yeah, it would be independent because it would depend on what value x2 we have, like sort of let's see, like
uh,
from single output we cannot like have a relationship completely.
what are you saying? Will it be dependent or independent?
Let's see. Like for x1 it should be independent, but again like the order in which they come, so
Okay, independent.
means like let's say if x1 is the first variable that we have, so for that particular variable it's completely independent, like currently the y what we have. But let's say x2 is a second thing, so that depends on like what x1 is, so that can like give the outcome of y. So y is dependent on x2, like given we have x1 in it. Like, so is it some order in this case defined, or like it's either x1 only if we say, like, or like kind of what is it
No,
like?
there is no ordering defined. It's just an XOR function. Uh, but yeah, you are sort of correct in the way that yeah, x1 is independent of y. So now seeing this function, it seems okay. X1 and x2 both are determining y. Then how is x1 independent of y? But because like for determining why we are both needing x1 and x2, so the causal model that we kind of draw in our minds is something like x1 and x2 both determine y. So but this is faulty here because since first of all yeah, let's say I told you x1. So how would you go about proving whether two random variables are independent or not in a like this is obviously a categorical distribution sorry, discrete distribution, because x1 can take just two discrete values same as x2. And now whenever I write, please know that if x1 is, I'm saying x1 is a random variable, and x2 is also a random variable, and y can also take this two discrete values, so it's a discrete distribution. So initially probability of x1 is equals to x is half, where x is either 0 or 1. Same for x2 and same for y. If you go, then there are only two. Yeah, if you can see, the probability of each one being 0 or 1 is half. But now when I say okay, probability of y given x, so now when I say yeah, y given x, then let's say I told you y is equals to y given x1 is equals to 0. Even when I told you this x1 is 0, then now we are only looking at these paths, and still the probability of y is half. Y can be 1 or 0. It's still half. And probability of y given x2 is also x2 is equals to 0. Then this would be again these and these rows. And again, it's like still yeah, it's still half. So it's either, again, it can be still 1 or it can be still 0. So even this is half. So while proving independence for this discrete random variables, what you need to always ensure is you can't just like see the causal uh, get the independence from like the causal model in your head based on seeing the variables in your mind. You need to always
Final, if you can hear us, I think you're frozen for me at least.
Same here as well.
Okay, you're back.
okay. So were you able to wait? I'll switch my internet connection. Yeah, now it should be better. Yeah. So what I was saying is that sometimes you would think that the variables are dependent, but you what you need to really do is sit down and check the values for every value that x1 takes. Is it influencing y or not? What probability of y is equals to y given x is equals to x1 should be equal to probability of y is equals to y. Now this you need to check for every x1 and y, all the pairs that of x1 and y that can exist. So in reality, in order, like sometimes we know the story, and as I was saying, it might be easier for us. But in order to validate our assumption that the two variables are independent, this should hold true for all x1 comma y. That where x1 is belonging to realizations of x, and y is belonging to realizations of random variable y. now you can see how why is it a difficult problem, right? So because there might be just so many pairs, and now this is just for checking the independence of y with x. Then you need to again check it for y with x2, and with all the again with all the pairs. And this is like a simple case where there were just two realizations of like two observed value for each random variable. In reality, if it's a continuous variable, then you can see how it's like it's basically hard problem to solve. When you know the story, it's easier. But now when I say, okay, now I'm giving you a function of probability of x and y, some function of x comma y, and then to see, okay, there are a few tests, but now again, it's basically just when we are including two continuous variables, it's basically a hard problem to know whether these two variables are really independent or not. So yeah, that's what I wanted to say. So and then these kind of relationships like show up in many places. Like I think the Windows troubleshooter used some kind of probabilistic graphical model to denote yeah, the causal relationship between events. And sometimes yeah, when there are just so many nodes in your variable graph, it might be not intuitive to know which variables are independent of each other. But where knowing this sort of independence helps us a lot uh, in causal influence, in knowing which variable is affecting others. So, and that's a whole other field of probabilistic graphical models. So, yeah, yeah. If you are interested in this sort of thing, I would just mention, yeah, there is this good course on Coursera on PGM. Professor Tafni called. It's a great course on probabilistic graphical models, and there are these notions of like how would you go about knowing whether these two variables are truly independent or not, and defining relationships between all these variables. Yeah, we would not go into depth yet. Then the other notion is of conditional probability, and I think you all might know, so I won't go into depth here. I just want to give you some sort of this is called marginal probability. These are the terms that you will come across in the literature, and just know that yeah, this one would be a joint probability. So whenever someone says joint probability of x1 and x2, you should immediately know that what they are talking is probability of x1 comma x2, and then this is conditional probability. That's it. I won't go into depth here. Then another thing is chain rule of probability. So yeah, from this we can immediately see that probability of x comma y, just from here, is probability of x given y, probability of y. And then we can, using induction, we can just keep breaking it down similarly. Like if probability of, I'm given probability of x, y, and z, then first we can write x comma y z, probability of y z, and then we can even break this down further, which would make it probability of y given z and probability of z. And here you are making known assumptions of whether x and y are independent or not. So you can break any of these random variables are independent of not, and so you can break it down further and like form a chain of all the random variables. uh, yeah, that's basically why it's called a chain rule of probability. So in general terms, it would be probability of x1 to xn would be something like probability of xi given x1 to xi minus 1, and I go somewhere. Yeah, and here at least you are no making no assumptions of whether any of these x1 to any of these xi's are independent or dependent on each other. This is a general notion that holds true for any values of these random variables. Then the other thing that I would like to add is some rule marginalization. Yeah, and this is the sort of thing that we mentally do a lot. Uh, like even when I say, yeah, so let's say probability of x is, I don't think I would be able to find a really good example, but formulaically, it's simply if uh, either sum of probability of x comma y, if y is a discrete probability of x is equals to x is equals to sum of y, probability of x is equals to x and y is equals to, yeah. And this is assuming y is a discrete random variable, or otherwise, if y is continuous random variable, then it would be this. So basically, what you are doing is, let's say, this is your overall total space, and this is what probability of x is, and like this is what basically denotes uh, x is equals to some value x, and then you are, along with, now you have some value of y, and it's basically partitioned like this. You, what you are doing is, when probability of x and y is this, probability you're summing up all the possible values that y can take along with x, and then you are just adding all of them up. So even when like doing Bayesian like solving simple problems on Bayes theorem, what when many a times what we do is, in order to calculate the probability of, let's say we are interested in y is equals to y given x is equals to x, then yeah, this is just probability of x comma y, and here is probability of x is equals to x. And in order to calculate this, what we many a times do is generally just take a summation, assuming y is a discrete random variable. You would just take a summation of, let's see here, it's y hat, and this is again realizations of random variable y. Generally, in order to calculate this denominator, you would marginalize out the variable and basically take all the possibilities in order to get probability of x is equals to x. And with all these concepts, you should be like completely familiar with all of these concepts, because everything that we are going to be doing is basically building up on all of these. Yep. And one last thing, won't go into depth much here. Simply Bayes theorem, fundamental theorem that all of the Bayesian statistics is built on. Let's say I have, now whenever I write theta, or I would just write here y, but whenever I write theta, first think of it as some random variable rather than like a parameter which you would like, which you would implicitly assume because of all the prior knowledge that you have on machine learning. But now we are generally all dealing with yeah, just random variables. So this is this, and then this would again, you can also write probability of x y as x given y into probability of y divided by probability of x. Now this is called a posterior, Again, some terminology which you all need to be familiar with. This is sometimes called as likelihood. This is called evidence, or you can also call it marginal, and this is your prior. So yeah, that's all what I wanted to say about fundamentals. And now, um, any doubts earlier that you have? Okay, assuming not. Uh, so now we would start with the Bayesian learning. So generally, whenever for statistics, there are basically two main approaches solving problem. One is frequentist approach. The other is this Bayesian that we are going to study about. Uh, for frequentist approach assumes that okay, now there is this fixed model of the world, and you are trying to observe this data and making sense of it. So if I would give you an example, yeah, you're flipping a coin, and then you want, okay, what's the probability of it just going to uh, sorry, land heads, and then what a frequentist would say, okay, I know that the probability of so it's basically a Bernoulli distribution with zero point 0.5 probability. So the frequentist would say, okay, uh, it would assume a distribution on the variable, and then it would try to get the prediction and basically do some sort of analysis. So here he made an implicit assumption about the world. Okay, it's going to be uh, the coin toss is going to be follow Bernoulli distribution of with zero point 0.5 as a parameter. Whereas what Bayesian would do is it would get the data, try to try to obtain a distribution, try to obtain a distribution over the parameters. It would see all the other random variables. So basically, it won't assume that the probability of x is equals to heads is zero point 0.5 implicitly. This won't be assumed here. It would be like calculated, seeing the data and taking all the another sorts of other variables around it, maybe like the wind direction and whatever it can take into account. And then it would try to, yeah, it would basically try to first find this parameter, let's say theta, to try to guess this, and then it would try to fit a model. Whereas a frequentist would, yeah. So another example of it is hypothesis testing, and as we like for hypothesis testing, we just directly assume that okay, it's a normal distribution, because in frequentist approach, that's what we do. We kind of make our assumptions about the implicit distributions and then calculate the parameters, whereas the Bayesian would include all its prior knowledge and basically do a full inference on all of the available data and then try to guess the parameters of the model. That's kind of a vague distinction between the two. And now we are all basically going to focus on this Bayesian approach. So
Fenil. So, like in a way, Bayesian, we can assume like it's sort of a simulation in a way, so where we kind of basically do some trials, and based on the trials, like whatever we get, like sort of results, we try to hypothesize that particular thing. Whereas in frequently, it's more of like we assume everything as like sort of a unbiased or like some sort of a prior knowledge, and based on that prior knowledge, we directly assign like probability in a way.
yeah, so sort of correct. So basically, it let's say we would see this in later part, that if let's say if I'm tossing a coin and I got 8 heads and 7 tails, then my Bayesian approach might tell me that the probability of getting a heads is 8 by 15, because now what I'm learning this parameter theta with the help of the data, whereas a frequentist has already made some assumptions and then it's doing analysis on those assumptions. So basically, Bayesian removes any assumptions of the world that we might like have, and that it incorporates those assumptions, but it doesn't like directly give us a distribution on those assumptions. Directly doesn't it give me a distribution using those assumptions? It would try to learn those parameters of the distribution that we have.
It's easier to clarify in the extreme case. Like this comparison is more memorable. If you toss a coin 8 times, or let's take your 15 times example, and it comes up heads all 15 times, then your frequentist is going to think tails never exists. So it's only going to be heads all the time because that's what the data tells me. I tossed it 15 times, I got 15 heads. Whereas the Bayesian is going to be using some prior knowledge of the world and saying, look, a coin has two sides. At some point, one side has to come up. And so I start with the assumption that the coin is unbiased without seeing any data. That is my prior knowledge because I've seen other coins in the world. It's not based on any data about this coin. But now I start seeing data about this coin, and now this coin tells me 15 heads. So in the same case, the Bayesian is going to say, okay, heads is definitely more likely, but it's not impossible to expect a tail to come up because in general, I've seen coins and coins do flip tails sometimes. So even if heads is far more likely, tails is not zero. Whereas the frequentist is going to say, look, data tells me tails is zero. I'm going to take tail zero.
Yeah, that's better. So yeah, and so now we use this Bayesian approach to solve like focus would be like to solve the problems that we come across. So now let's say yeah, so we have this x train and these are the variables that I'm just introducing, which we'll be using. This is y test, and then there is this parameter uh, theta that we are trying to guess estimate about the world. So now, first of all, when we have all this flow of machine learning methods and like I would like to stress about why we are using Bayesian approach first of all. So first of all, let's say we have some neural networks and we have this weights. Uh, Now any machine learning model can directly just train on this and obtain these weights that are good for prediction on y. So like and but why to use then these Bayesian approaches? So a machine learning model can tell me these weights, but it won't be able to tell me the distribution around those weights. Now, let's say what would happen if I change these weights slightly. How would my model perform? Let's say I have this. It told me this is some. These are the weights that are giving me the best possible value of y. But how is this distribution? So basically, there is no notion of uncertainty in that. It can be like that. It can be like this. All of these give us the best performance and with these values, but we don't know how of how our model is affected by those weights. How our model is stable across those weights. So this is one of the problems that doing a full Bayesian inference would be able to solve. It would just give you an entire distribution. You can just do and then sometimes if the model is like this, sometimes you might not be interested in these weights, but you might be interested in these weights. But the model won't ever be able to find such weights like simple a machine learning method because these even though these are more stable, it gives us optimal performance at these values. So machine learning model won't be able to give you won't be able to give you a distribution and then any other sort of analysis that you want to do on those weight vectors you won't be able to do. Whereas a Bayesian inference, a full Bayesian inference would help you with that. That might be one of the motivations. There are many other different reasons why Bayesian learning would be helpful. Yeah, you can look it up. So let's say if we are trying to solve some sort of classification task, then what we would try to do while training is to get this some parametric vector theta using my training data. And this would be for training. And for testing, we would probability of one y test given x train, y train, and theta. This would be something that we would be interested in doing while testing. Oh, and also x test. So now, wherever I mentioned these, assume all of these as random variables. X train is so typically you would have say n n n data points and m features. Now, always assume that these data, these if there are m features x1 and x2, then x is my random variable, a multivariate random variable with x1, x2, and x1. All of these are my kind of univariate random variables. It's a vector of random variables. That's what a multi-dimensional random variable is basically is. So, and all the data points that we see are basically some sort of sampled values of the distribution of x. So that's what I would like to take, like think you about whenever I mentioned x train, y train. Theta, again, theta is some parameter, but at the same time, it's also a random variable whose values we are predicting. And basically, this distribution of theta that we would love to get, but it's quite difficult to get. But yeah, so and since now again you are defining a distribution, so assume theta as some random variable, and it won't be just a single value like what we are uh, kind of trained to assume and because of like all the machine learning courses that we did previously. So these are the two quantities that we're interested in. For and this is like for not specific for any kind of supervised learning task where you have x-train, y-train as data and you want to predict on y-test. This is kind of general framework. So how would you go about first probability of finding theta given x-train and y-train? So you would use a favorite bias theorem here. This would be something like x-train, y-train given theta. And at any point of time, if you are confused or if I might write something wrong, just feel free to unmute and just point it out. Then yeah, we can break this down as probability of y chain, just chain yeah, chain probability. Then even we'll be able to break this down. Extreme, this would be extreme probability of yeah, extreme, yeah. Mm, yeah, but now this x train is sort of given to us, and we would assume it uh, like independent of theta because yeah, the X train, the data that's given to you is going to be fixed. So we can just remove that, and I would actually switch this around. Y train, this X train, then these and this. Okay, sorry, so this might be confusing. So instead of probability of X train given Y train times Y train, I've switched it to Y train given X train times probability of X train, and then this and this gets cancelled out. So this is what we are focus is while training. Yeah. So we'll see a couple of problems on this on like simply how a first simple case of linear regression of how to do that, and then for testing we are interested in probability of y test given x test x train y train. Now we can again do full Bayesian inference on all of these. So it's just um, yeah, theta x train x, this is d theta. So this is nothing but marginalization of probability for all the values of uh, parameters theta, what the value of yts might be, just marginalization theorem. Then again we can use Bayesian probability here. This would bias given xts extreme theta times probability of theta given xts. Now bias is kind of only dependent on x training set and theta. It won't be affected by x train. So it's kind of an independence assumption that we are assuming that, yeah, since in order to define y, this is ts. On the test set, we only need the random variable x of test set and theta and nothing else. This based on an independence assumption. And then again, theta is only defined by using x train and y train. We won't use the training test set for getting the theta. Again, this is equivalent to this basically, and hence a probability of y test set given x test set, x train, and y train would be a full Bayesian inference on my. Yeah. So what you, in order to get the real estimate, so what you would do is take every possible value of theta. So yeah, let's say theta some real on real line. Let's say first I pick this, then I would ask the question, given my training set, what's the probability that I would observe this theta first of all? I would observe this theta. Then this is what that is, probability of observing that theta given your training set. And then, okay, let's say if I observe this theta, then how would it contribute to getting the probability of y test that I was given? So using that to, so kind of you can assume this sort of graphical model. Y test set. Yep. First obtain this, then probability of finding this theta, and along with the test set that I was given, what would be the probability of seeing the y that I'm seeing. So yeah, and then you would do this for all the possible values of theta. So you can see why this would be a hard problem, right? Because theta not here, it's if theta is just a univariate variable, then a one-dimensional variable, then it would be a simple integral. But let's say if theta is theta is basically your weight vector of a neural network, say, and then if there are hundreds and thousands of parameters, this would be a multi-line integral with thousands of, like, basically you would stack thousands of integral in order to just obtain uh, the value of in order to obtain the probability of the test set that you see. That's why it's an extremely hard problem to do this, unless we like kind of assume some kind of implicit structure on these probability distributions, assuming it's a normal or something like that. So I want you to understand why this is such a hard problem. So here I have just drawn a single integral, assuming that theta is a real number. But if and this is never the case. We never just want to estimate a single parameter. So, and whenever it would be yeah, if it's basically if belongs to n dimensions, then this would be n integrals stacked one after the other. So but this is simply the goal of Bayesian learning, to estimate these two quantities. First, simply to obtain the parameters theta, and then to do testing, you would do this. Then we can, yeah, and sometimes using this, just this training procedure, you can also do kind of an online learning. So where, let's say, I have at kth time, my prediction of theta is nothing but this is x car, all that k is kind of, I would write t in order to make in current time step. X train is okay. T is at the time step, not training or testing or anything like that. So I've observed these x t amounts of data till now, and this is nothing but probability of x t given theta, probability of t minus 1 of theta given probability of x. So this is your prior knowledge of theta till t minus when you only saw t minus 1 at t minus 1 time step. Then you saw some new variable, basically a new data point. Then you can update your prior on theta accordingly. So as new data points come in, you can keep updating your parameter, your prior on the parameters theta. So one of the benefits is you can do this sort of online learning and keep updating your yeah your distribution of the world. So theta is nothing but some parameters of a distribution. Then yep. So in the lecture there was this like if you go in the Bayesian course, and there is this sort of Bayesian networks and probabilistics model and all, which I'm skipping. But yeah, as I said, this probabilistic graphical models would be a great course for you to learn more about that and in depth. So now let's do some problem on estimating this. So I'm assuming you all are all aware with multivariate distributions and multivariate normal in particular. Just kind of like taking an excursion. So this is all about multivariate normal, because we'll be using this a lot. Here, x is your random variable, and now it's a n dimension vector instead of just a single value.
I sort of missed the switch, but like maybe it's worthwhile for like to pause for a moment and maybe one or two people could try and sum up what you gathered from Bayesian machine learning versus regular machine learning. Um, and maybe also sum up like what frequentist versus Bayesian means to you. And it's completely okay to be wrong. In fact, it's encouraged to answer like have a high variance in answers, and that's perfectly fine as opposed to no answers.
And yeah, I was hoping this to be interactive, but yeah. So please go ahead.
Um,
Yeah.
ठीक है, Jay, go ahead.
So like for frequentist and Bayesian like statistics, so the major like kind of in a way the overall point is for frequentist it's like based on like we're given some data, we draw observe like kind of observation not exactly observation but so based on that given data we perform some experiments and we directly draw like conclusions from that data, whereas like the Bayesian where statistics focuses on some prior knowledge and performs some experiments but never basically comes to a conclusion, like it sort of updates based on the evidence as it gets like that way. So it's a constant learning process like kind of in a way like what I can kind of get from this particular two different statistics approach. Maybe like someone can correct like if it's wrong.
Anyone else for that question?
I think I like the example Swapnil gave. So if we got a dice and if we see the dice always got one, if we throw it for 6 times, in frequentist we would assume that it would always get one. But Bayesian would always think no, it's only 1/6 chance because it will use the prior knowledge that it has 6-sided, so it shouldn't be one all the time. So I think that's the main difference between Bayesian and frequentist.
Anyone else?
Yeah, I wanted to talk about the difference between Bayesian machine learning and the normal machine learning. So that uh, the most important part that I could gather was that in machine learning, you're ideally just looking for the most, just one set of weights. And once you've got them, I mean, okay, I'm happy. That's all I want. But in Bayesian machine learning, you're trying to understand the distribution of those weights itself, so that I mean, if you don't necessarily want just one set of them, and how changing the weights themselves affects the distribution of the uh, I think
Take your
you
time.
get.
Take your time.
Yeah.
This is great.
Uh, yeah, I think that of yeah, I think that's what I was talking about. I mean, that one figure that Fennel drew that really sort of put it into perspective. Uh, where there were, I guess, two crests. So yeah, this one. So that was what I remember distinctly. So I think that covers it.
That sounds great. Anyone else for question 2?
I think in Bayesian they take the average of the weight, but in non-Bayesian they would we would only have taken the weight which is like the best weight or the one which has the highest probability rather than like taking the average distribution of the weight.
When you say average, what do you mean?
Like for example, like it's not a just a like it's the average of all the weights values.
Okay.
Does that make sense?
I'm not sure, like, if the average comes from this notion of integration, then I think I understand what you mean. Like,
Yeah,
that's the
yeah,
average.
yeah. That's what I meant. Like it's marginalizing it.
Mm-hmm. But you have to remember that you are not averaging your weights, but rather trying to say across this space of models, which is the best model that gives me my predictions, or that best describes this data set. So you're averaging, you're right that you're considering multiple weights, but like you're actually considering multiple sets of weights where each set of weight corresponds to a model in a hand wavy sense. But yeah, like you're not averaging all the weights for a single model, you're averaging multiple models for a single problem of interest, for a single conditional distribution of y given x.
Right. Okay. That makes sense.
Anyone else for question 2?
So like
Sorry.
so like how is it different from like in a way ensemble models kind of in a way, like if we see from machine learning perspective where we have different like weights and different models and we're trying to average it out, or like we see based on all the data we have we try to have this thing predictions in a way. So how is it this is different from Bayesian, like if like as per your kind of definition, if we see like we are kind of trying out different models and trying out seeing out the weights and like then figuring out the final thing.
That's an excellent question. And to my understanding, an ensemble would mean you are considering multiple models simultaneously. Whereas in Bayesian machine learning, you still end up with a single model, but now you know how uncertain you are about your weights. So if the distribution over your weights is like relatively flat, then you know that okay, these weights are not these weights are highly like could vary a lot. Whereas if this distribution is peaked, like one particular value of the weights has really high probability, then you're like, okay, like I'm very certain that this weight is right, or and so on for the set of weights that I'm talking about for a particular model. And so like you will you can still end up you usually still end up with a single model, like you want that, but you want to know how uncertain you are. Whereas in regular machine learning, you don't have that. You just end up with a value for a weight. You don't know what other values the weights were taking unless you track how those weights change, and then
Okay.
when you're tracking, then you're essentially just like seeing the
So,
distribution of the weights.
so maybe it may be interpreted as like in machine learning way of doing these things are like, okay, let's say we get some local minimum or something like that way. If it's like not changing, it's the best like that we have so far. We stop it. But in Bayesian space, Bayesian statistics, we try to search all the like minimas in a way or like something like that. We kind of like all the hypothesis space. Like we are not getting stuck at some local minimum. Maybe like this, but I'm not sure. Yeah, like this is very hand wavy.
Yeah, I think the technical term you're going for is uncertainty.
Yeah, yeah.
Yeah, and that's perfect. Like you want to know about the uncertainty of your distribute of the weights that you have arrived at. Like how sure are you these are the right weights? How sure are you these are not the right weights? And this distribution over the set of weights tells you exactly that.
Okay.
Okay, that was an excellent discussion. Thank you. Thanks, Fanel. Please continue. Sorry for the interruption.
Yeah, no problem. Yeah, I would say please interrupt me. I would feel better. And yeah, so as like I would just like to add, Jay, what you were saying is correct. But in ensemble, for every model, we would try to find the best sort of weights. But here, while doing this full Bayesian machine learning, we are kind of like, even if there is this yeah, even if let's say there is this very bad weight which is not contributing anything and which is saying there is very low probability of observing your y, observing your test set, but still you would consider this like okay, even though there is a very low probability for that, but just tell me uh, how likely my data, the test set, basically how likely it is, because you're doing kind of a full Bayesian inference. You're trying to do take into account all the possible values of theta, however bad it is. So that's a kind of a difference in both of those models, in ensemble machine learning and in full Bayesian inference. And also, as Deb was mentioning, taking the average once you have these, once you have the entire distribution, and sometimes it would make sense to rather than using uh, in simple technical terms, what a machine learning model would do is find the mode of this distribution, whereas it would make sense instead of getting the mode to use the mean of the distribution rather than using the mode. And sometimes this would give better. I have one example planned in order to demonstrate why mean sometimes would be a better estimate of our parameters than the mode. So sometimes it's better to use the average values of the weights instead of like the mode that gives you the maximum. And so what I wanted to do is give an example of these training and testing procedures for linear regression. Then for that I would require some sort of like because we would assume normal distributions. So that's why I wanted to first like go into this excursion into multivariate normal. Uh, yeah. So this is x is some x is random variable, n dimensional random variable, and whenever an n dimension random variable is simply n different variables, n different univariate random variable stacked together. So so it's kind of like if I'm saying you probability of x, then it's kind of joint probability of x1, x2, where x is these n random variables. So now if this n random variables are uniformly distributed, uh, sorry, not uniformly distributed, are normally distributed, then then the formula of normal distribution, this is the mean vector, and this is the covariance matrix. Yeah, I am assuming you know this already. This is square root and this is square root, and this is a determinant of the covariance matrix, x minus mu transpose sigma inverse and x minus c. Yeah, so this is basically the PDF of normal distribution. And so one small thing is whenever I give you a distribution or something, it would be a good homework practice for you. Really see whether it's a distribution or not. Try to integrate it. And there is a good amount of learning curve in that. So try to integrate simply a univariate normal by yourself and see whether it's giving you it's giving you a one or not. And then you will also realize while proving that the difficulty that it arises when you are not doing minus infinity to infinity of normal would give you one. But then let's say if you replace with x, and then you would realize the difficulty it comes up when like uh, guessing a functional form of x and how difficult it is. Then then it's a homework problem would be to go ahead and integrate a normal to see what value it gives you. And then you'd realize, okay, y error function, and uh, there is no simple single formula of yeah CDF of normal. But anyway, so this is your PDF of a normal distribution. Sigma is your covariance matrix, and this is just uh, so if x is this vector of random variables xn, then nu first initially would be expectation of each of these random variables. So stack vector of all of that, and this would be a covariance matrix. Now, properties of this covariance matrix. This is very important because one of the problems you would see is whenever you are optimizing whenever you are say taking this optimizing this in order to find this parameters new and covariance for your normal. Your new can be anything, but you cannot have n by n random matrix that you can call it covariance. So covariance matrix has certain properties, and only if it satisfies those properties, then only you can say, okay, it's a covariance matrix. So yeah, it's one of the common problems that you face while optimizing a normal. You can simply do you can simply put differentiation and find the new vector. That's relatively easy. But yeah, whenever you are finding this, then these are the set of constraints that you need to keep in mind. So first of them is symmetry. That's easy to see. Covariance of x1 comma x2, same as covariance of x2 comma x1. So these and these the values are same. So it's n by n matrix always. Yeah, I hope that's clear. And then yeah, so it's always symmetric. And second is positive semi-definite. Now, uh, is anyone not aware of what positive semi-definite matrices are? Or
Ask the opposite question.
yeah, so okay, can, can anyone tell me what a positive semi-definite matrix is?
See?
I'm not sure whether they are just like shying away from answering or okay. Uh, so I wanted to go and prove why symmetric matrices are positive semi-definite. But first, I think I need to show you what positive semi-definite matrix is. Uh, so a simple way would be like if A is your matrix, there are multiple tests of positive semi-definite matrices. See, one of those tests is X transpose. Okay, now A is a n by n matrix, and X is n by n vector. N vector. This should be always be greater than zero, uh, and yeah, for all of the X that belongs to R. So yeah, why are we interested in this some random phenomenon of like multiplying these vectors and saying it should always be greater than zero? So you first of all, it's kind of an interesting one of the interesting properties is if you if a x is a vector, and then if ax would give you uh, a transformed vector, so assuming this a is some kind of a transformation, yeah, you can interpret matrix as a transformation, and you would realize if you had gone through the reduced attired length of 3 blue 1 brown. So yeah, if you assume that as some kind of transformation, then this is first of all see to it that you understand that this is always give you a one dimension a real value, and it won't be a vector. So this is 1 cross n, this is n cross n, and this is n cross 1. See to it that yeah, so whatever quantity I write, it first of all it should be in your head makes sense. Okay, yeah, is it giving me a vector or a matrix or a simply scalar value? So here x is a vector, a is a matrix, and this quantity it should always be greater than zero. When now a of x is some transformation of x, yeah, and then when I this and when I take the dot product of it, so this is some vector, and then I'm transforming it, and I hope x dot product of y is same as x transpose. So I'm assuming you know this. So, but basically, my original vector and my transformed vector, the dot product is giving me a positive value. So it's kind of my matrix is not flipping. This would only be positive value when the theta distance the theta is less than 90 degree. Theta is less than 90 because this is this cos of x, and cos of angle theta is angle between x and transformed vector. It's sometimes this positive semi-definite matrix is like you have a vector and then you transform it, but you really want to know whether that transformation is completely changing the direction of my initial vector or not. So in that sense, positive semi if the matrix is positive semi-definite, it ensures that the transformation is such that your value, you are not basically, by transforming it, you are not flipping it in the opposite direction. You might change it, but you are not flipping it since the angle between them is always less than 90 degrees. Hope that's clear. So there are some tests where you can say how you can ensure that matrix A is semi-definite. First of them, as I showed you. Now, for machine learning, for Bayesian purposes everywhere, whatever linear algebra we use will only be focused on the matrix obtaining real values. All of these also have a correspondence when the matrix has complex values. But all of those linear algebra, I don't think we ever need that. So yeah, so all of these just have real numbers currently. So yeah, first of all, one of the tests is if you can prove this for all x belonging to Rn. Another test is A should have uh, positive eigenvalues. And now, please tell me if you already know this so that we are not repeating stuff and yeah, we are not wasting anyone's time. But all of these, there is this one lecture on positive semi-definite matrix. It's like a fourth or fifth lecture by Gilbert Strang in the MIT lecture series that Swapnil provided in the link. So yeah, these are like two common tests, but then there are like 3 to 4 other tests as well. But sometimes like this is the most, since the definition of it arrived from this is the most used test, and you can find a correspondence between all of these. So yeah, but then um, yeah, if you want, I can like simply prove this. It's just a simpler proof. If A V is lambda V, of course, B is an eigenvector. I hope you know the definition of eigenvector and eigenvalues. Lambda is a scalar, that is the eigenvalue. And then if you are doing this X transpose AX, what you are basically, if X is your as I said, X can be any of these, X can be any of this value. So let's say we replace X with the eigenvalue, eigenvector, sorry. This would be V transpose AV. But now AV is same as lambda V transpose lambda V. We know this is positive. We know this quantity is greater than 0. And this is same as this. And that, so now lambda is a scalar, so that you can take that out. This is VTV. This is nothing but, yeah, if dot product of V and V, this is nothing but mod V square. Yeah, because angle between them is 0. This is positive, and hence lambda should also be positive. This implies the other, hence lambda, you should always have positive eigenvalues.
Is it positive or is it non-negative? क्योंकि
Uh, uh, so if A is positive semi-definite, then this greater than equal to would change from for so positive semi-definite, lambda can be 0 or any positive value. Yeah, you are correct. Sorry for that. And for positive definite, you remove the equal to sign and ensure that it's always greater than 0. So should have 0 or positive eigenvalues. A is a positive semi-definite matrix here. Correct. So yeah, so there are a few other tests as well. You can see that in your own time. But yeah, so these are the two tests. And now, why is symmetric matrix positive semi-definite? It's the question. So sorry, why is a covariance matrix positive semi-definite? Covariance matrix is I hope this is you are aware of this calculation. This is how you define a covariance matrix. X is your R cross N. Nu X is simply this your mean vector that I mentioned earlier. So expectation of x1 to xn, again R cross N. And now know that this doesn't give you a scalar, it gives you a n cross n vector, because this is n cross 1, and again this is 1 cross n. So this gives you an n cross n vector. And like expectation of a vector, expectation of a matrix is just you take the expectation inside and take it on an individual element. If yeah, if it's x1, x2, x3, x4, then this is nothing but expectation of x1. Similarly, so this is how you would define a covariance matrix, and you can see if this would result in getting the individual covariance of x1 with x2 in the in the first column or first row. So this would result in that. But now we need to prove that this should be greater than 0. So lambda, empirically this would simply be I is equals to 1 to n xi minus x bar, xi minus x bar. X bar is the new x. And now if this was difficult to see how this is a covariance matrix, this should be simply very easy. If I'm just taking ith row and jth column, then what I'm simply doing is take the ith row of the yeah, basically for kth value, take its ith feature. And again, this ith feature for this. And here now take the jth feature and take its transpose. I might have made it a bit complicated than it initially was, but if you expand this out, then you would see this would just not give you nothing but covariance of xi with xj. Here xi and xj are single dimensional random variables. x1, xi, xj, xn, and something like this. So yeah, so basically covariance matrix is this, and now if I'm saying that okay, it's a positive, why it's a positive semi-definite matrix, let's say why this is basically the first test that we are using for all the vectors. This should give us positive quantity. So why instead of x I'm using y, because x is a random variable for the covariance matrix. This would give us
I just एक बस छोटा सा डाउट है वो जो ऊपर the x bar that you've written is that is the same as the mu x that you used मतलब that is
yeah,
mu x only right
yeah, yeah.
yeah okay हाँ correct sorry
So y transpose 1 by n, and I'm just rewriting this formula. This y. So this would be 1 by n y transpose xk minus x bar. So I took them within the summation. If you can see, this is nothing but y of xk minus x bar का transpose, the transpose of that with mm, sorry, it's xk minus x bar transpose of y. Yep. And then this is the same as this. This is xk minus x bar transpose of y. So AB transpose is B transpose A. So this would be Y transpose, A transpose of transpose is A. So you can see this changes to this and this changes to this. So we are taking dot product of that. Let's say uh, some vector P is equals to xk minus x bar transpose of Y. Then this is simply P transpose P, which is nothing but P dot product P, which is nothing but mod P the whole square, which is always positive. Sum of all the positive values is positive. Hence, this quantity is positive. Hence, yeah, hence sigma is a positive semi-definite PST. Okay, now whenever I say positive, it includes zero as well because we are trying to prove it's positive semi-definite matrix. So this can be greater than equal to zero. So any doubt in this? Okay, so I'm assuming that's clear. So yeah, so these are the two main properties, and any kind of optimization you do on a normal or anywhere, if some matrix is a covariance matrix and you need to optimize for that, these are the two conditions that you always need to ensure. Otherwise, if the optimization gives you some basically some random values, then that would not directly correspond to a covariance matrix because yeah, if it doesn't ensure these two properties. So this is all I wanted to say about multivariate normals. And now we would kind of yeah, go back to where we were and see yeah, so let's say now we are trying to do a linear regression from Bayesian perspective. Okay, yeah, so next topic is linear regression. So here, as we said, what we are trying to estimate as shown here in X training data set. We are trying to estimate this. Given X train and Y train, what are the probability of my weights? And this corresponds to this. I hope these proofs were clear to you. If there is any doubt in any of the previous sections, yeah, I'm fine to go over them with once again. So yeah, we are trying to estimate this using this. So now let's say theta, my weights of the linear regression model, then I need to find probability x and y. I'm removing the subscript training because we are just trying to find the optimal weights given this training data. Yeah, so I'm then this would correspond to y given wx, probability of w. I'm hoping you can see the correspondence between these two. This is probability of w, y given xw, and this is y given x. This is all what we are trying to estimate. Now, when I say we will be doing full Bayesian inference, doing full Bayesian inference is very hard. So again, then what they generally do is, because it's so hard, we again remove that. Okay, let's say first we are not trying to find the entire distribution of W. But let's say now we just focus on the mode of W. that's what we do, because essentially if we are because then the problem becomes very easy. Now if in order, if you need to find this probability of W, the entire probability distribution, you need to estimate. And as I said, estimating this involves solving an integral, and it's not just a single line integral, but if my it's n feature vector, then n different integrals stacked together, and that's also dependent on the function as well. That's very hard. So now what we would do instead is just solve for W that gives us the maximum value. And interestingly, what this does is, this is since this is independent of W, we can discard this. When and you can discard only this when you are just like optimizing for W. But now realize that what you would get out is just a single value of W and not the entire probability distribution. Again, we are kind of moving back to what machine learning people do. But and then now what you need to do is maximize for W this value. So the W, what value of W would be most observed when I have X and Y as my training data. And again, yes, still here we have no we haven't made any assumptions about the model is linear. But now, yeah, now we'll do that. So I hope you understand this, why we are able to discard this denominator and at what cost. If we want to discard the denominator, the cost is now we are getting a single point value of W instead of the entire probability distribution. And
We discard this because it doesn't depend on W, isn't it?
yeah, but yeah, and so you are trying to optimize for W, and that's why you are able to discard it because it's independent of W. But if you want to do a full Bayesian inference and get a probability distribution of this, then you would also need to normalize it, right? This quantity isn't giving you the probability, because the probability is the entire thing. This quantity is just that it is dependent of W, but just some quantity which is not normalized because you have discarded the denominator. While optimizing it for W, it makes sense because since this is independent, we can discard it. But now the cost is that we won't be able to get the probability distribution of W. So, and even after optimizing it, what we are at the end going to end up with is a single point value of W. Okay, now you are trying to solve this, you optimize it, and then you find, okay, W hat is my most optimum value, which is going to maximize this probability. Now, the only information that you have is about W hat, and not, again, you have lost information about the uncertainty that it had around that. So that's the cost of basically discarding it. But while optimizing it, you can discard it, because now when you say you are trying to solve this problem, you are basically saying I'm just interested in finding the maximum value of W, and I'm not interested in finding the probability distribution of W. So and now this is where we'll make,
So
yeah.
like in this case, it's just we are like kind of reducing the hypothesis search space like for the optimal value of W, but like we are not exactly like in a way kind of sticking to one value right now, right? Like we are trying out like all the values of the W that we would have like in that particular space, and then like we stick with the one which is the highest, but like we're not searching the entire hypothesis space. Maybe this is the right way to understand, or like completely different.
No, it is true. So basically now what you will be basically doing is find a functional form of this, what this value indicates, and then you will be just optimizing for W, like similar to how you do in neural networks, take gradient descent or do it manually. So, yeah, you will be searching through the hypothesis space for the value of W that maximizes this value. But you
Okay.
are, yeah, and so this is again like from Bayesian perspective, since that's very hard, we are again moving little bit towards machine learning perspective, where we are just like now interested in finding the maximum value of that. So it's similar to how you do gradient descent of neural network for finding this value.
Okay.
So, what are the advantages of doing this over the machine learning approach, like finding the max, or is it just the same thing? Or are we
Mm,
finding any more information or insight into
no.
our?
You are not. So yeah, you will see it. Yeah, you will see how what at what point we'll end up. So
Oh,
let's solve for this, and then you will notice where we
okay,
are
okay,
going to end up. So
cool.
now we are making an assumption of yeah. Till here we didn't make any assumption about linear regression or anything. Now all of these, since all of you are from Shelley's stats book, all of the assumptions that she said of linear regression will come into picture here. So assumption one: probability of y given wx and p of w is normally distributed. So, and now since we are assuming the model to be linear, okay, no, let's this is mu one and sigma one, probability of w. So this is our first assumption. Second assumption is that um, yeah, the second assumption is that the mean, I would say this is distribution one and distribution two. Mean of one is yeah. So let's formally it would be mean of residuals is zero. So this is where we are saying that the model is linear. It's basically saying that nu one is nothing but y minus w. Oh, no, sorry, nu one is nothing but wx. So yeah, if in linear regression, then if this is a w, then all the y's are centered around this line. That's when you can fit it. I am hoping this is clear. So this is your x, and this is some slope w. Yeah, wx, and all the y's that you're trying to estimate. Basically, y the mean of y is the value of w that you are trying to estimate. Here we are making the main assumption that the model is linear, and the weights that we are trying to optimize are a linear function of y. So this is some correspondence to Salisi stats where our model is kind of this: E is some random noise, random Gaussian noise, and then this is our model. So if you take the expectation of y, then this would be expectation of wx plus expectation of noise. And then as even there, Shesh mentioned, we can assume if the noise is not centered around zero, we can move our model in such a way that it's centered around zero. Then even this ends up at zero. So yeah, so now our new one is W transpose X. So W, this is dot product, so it would be W1x1 plus W2x2 plus Wn(x). So now our mean vector is centered around, mean of one is centered around, is basically new one is W1 transpose X. Then a third assumption is there is no correlation between any dimensions. And this basically what simply does is makes all of these zero and makes all of these zero. Even in sigma 2, makes all of this zero. Makes all of this zero. So this is like simply there is always a way that you can transform it uh, into a new set of dimensions that give you such a covariance matrix. But yeah, so first, can anyone of you tell me now once since I made all the non-diagonal entries zero, so what are the set of conditions that I would need in order to ensure it's symmetric and it's positive symmetric? Yeah. Anyway, all the non-diagonal entries are zero. So,
So like the variance in this case would be positive, right? And like there would be sort of a positive correlation between the two same variable itself. So it is going to be having in a way like the diagonal values as more like in a way you can think of that diagonal values as eigenvalues. So they are like greater than or equal to zero. So it kind of satisfies that positive semi-definite part, and also like since it's the non-diagonal values are zero, so you're like it also symmetric on their way.
okay. So,
And sorry, one more question I had. So maybe like earlier also you presented in terms of covariances like that way, but usually in the problems that we solve, we try to is we have generally diagonal matrices, right? Like the covariance means like basically in the previous example that we had x1, x2, x3, so on, like let's say above example. So in that case also we assume that the data is IID sort of thing, so due to which we get a diagonal matrix again, right? Or is it sort of like
no, 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 no,
different?
no. Okay. So, okay. So the data is IID is like assumed when your data points are IID. So, assuming that let's say I have x1, x2, and x1 data points, and x1 is a feature vector of yeah. So x1 are my data points, and then x is a random variable that has m dimensions. So in multivariate case, we are dealing with m dimensions. Data is IID says these all values are independent, and this is and like people make a fuss about it, but this is kind of a assumption that you can make, right? That if you see a data point x and then you see another data point, then those data points are generally like independent of each other. Like it's in a number line when I sample value some random value x1 and then I'm going to sample some another random value x2. So unless I am making my sampling that it is dependent on the previous example, I'm just going to randomly sample this data point. So the data set that I am getting, even in when solving machine learning problems and all, uh, the images that we are getting, we don't assume that the second image is dependent on the first image that we observe. That's why we are able to shuffle data. And if second image was dependent on the first image, then while prediction, it would be helpful if we even take the information from the first image as well. So
No, like
these
what I
assumptions
mean.
complex,
Sorry.
but yeah.
Yeah, yeah.
So but now when I'm saying that the covariance matrix is diagonal, the thing I'm saying is that even these dimensions are independent, and this is a very strong assumption that I'm making.
Okay.
Uh, let's say this is my normal distribution centered around zero, and here what, and this one is x1 and this is x2. These are these dimensions, and these are not the data points. Here x1 and x2 are not independent of each other. Like when I say this is like a 2D normal, and when I say you, okay, this is the data point that I observed, you are going to get some information about x2 as well. So when I'm saying that this is the case, then it is one of the special cases when my it's completely spherical and it's not elliptical.
Okay.
Yeah. So this is a strong assumption, and it doesn't come from the IID assumption of the data points, which is comparatively less. This comes from the assumption that my dimensions are basically independent of each other. So all of my Gaussians are just the spherical Gaussians.
Okay.
Yeah, that's a very good question, and like it's very important to know the distinction between independent data points and independent dimensions. So yeah, and then my original question. So if non-diagonal values are zero, then it's always going to be symmetric. Uh, now, if for diagonal values, uh, I hope you know that for if a diagonal matrix, eigenvalues are simply the diagonal elements of the matrix. So all of these needs to be positive as well. So in order to ensure symmetric and positive semi-definite, if I give you a diagonal matrix, you just need to see all the diagonal elements, and if even any one of them is zero, then it's not a PST matrix. Yep. And so now,
It would be PST, right? Because we want non-negative values. Like it can have zero, right?
yeah. So
Still, yeah,
yeah,
yeah.
true. So when I'm saying like positive semi-definite, and then when I say positive, then the zero is inside there, even though I'm technically wrong. But yeah, I should say non-negative values to be precise.
Definite is greater than zero, right?
Yep, yep. So yeah, so you have to check only the diagonal should be non-negative in order to ensure positive semi-definite for a diagonal matrix. I hope that's clear because the diagonal elements are the eigenvalues. Now, so our third assumption is there is no correlation between any dimensions. So what this gives us is lambda is simply sigma 1 and sigma 2. All of these are zero in this. Then our fourth assumption is even all of these diagonal elements are the same. So now sigma 1 is sigma square I and sigma 2 is some s square. So why sigma square? Because again, it needs to be positive, and then sigma kind of also defines like standard deviation because all of these diagonal elements are a variance. Yeah. So this ensures both of these things, that it's positive, is uh, it's positive semi-definite and it's symmetric. And so initially, like if what are the case one, case two, just to ensure that you get it. Case one can be the normal is anything. It can be yeah, all of these are 2D normals. Uh, Anywhere in this space, it can yeah, the center can and then the second is the both of these dimensions need to be, yeah, needs to be independent. And then the third one is this is completely spherical. So if this is your axis of the normal, then this would ensure that both of these axes is perfectly independent of each other. And then when I say all of them are same, then it is completely spherical around the center. So you are moving from this to this using our assumptions. So now we have sigma 1 as sigma. So after all these assumptions, this new our normals change to probability of y given w and x is equal to normal of wx comma sigma square I, and probability of w is normal of uh, some mu to s square. Okay, is this clear? Any doubts still here?
Won't the sigmas be different for the first one and the second one? Or will they, I mean, you written sigma square I for both of them. So,
This is s, uh, s square.
oh, okay, sorry.
So and then the other assumption that we'll make is the last assumption, that even these weights are centered around zero. That this would be zero. So, yeah. These are all the assumptions that we made, and then we end up at this value. Now what we are trying to do is maximize this quantity. So let's do that. Maximum of w with normal of wx sigma square I, normal of 0 square I. Now this is maximum of w. Yep. And now one common thing that you would observe in this cases is it's if I am optimizing for some quantity, say maximum of k, some function of k, and then if I go ahead and instead maximize this log of fk, these and these are completely same, because like if fk is my some function, okay, no, log is function defined as this is 1, this is x, this is log x. Now you can see that this is always increasing. So the optimum value for x, as x increases, log x increases. So, so whenever I change for maximizing to a log, even when this would be maximum, even this would be maximum, the log of this function, because it's kind of always increasing. So from this, yeah, and when I say increasing, I mean monotonically increasing, that at all points it's increasing. And I, yeah, so I hope this is clear to you. So we can always, and this is a standard trick that we'll observe, that we, instead of maximizing this, you can instead maximize log of this. You can try at home, both will give you the same answer, but in the later parts we'll see that maximizing the log is computationally easier than maximizing this entire value. And also then there is this also problem of, since each of these values are very small, then log would kind of bump it up to ensure that you don't go into floating point issues while computation. But it's basically we are not making any assumptions here. Maximizing this is same as maximizing this. So now we are maximizing log of first normal plus log of second normal. Now I would put in those massive formulas of normals. So now it's uh, this first part I'm just okay. Um, where did I write the formula of normal? Yeah, since this part is independent of w, I'm just assuming it to be a constant. This is what we are interested in. So this is log of constant exponential of minus half. First normal is defined on y, so it's y minus w trans. The new is w transpose x, so y minus mean of that. Sigma square I, the inverse of this is nothing but 1 by sigma square I. Yeah, I hope you know this. And then again, the transpose of this y minus w transpose x transpose plus log of this second normal, again c2 exponential of minus half. The mean vector is 0, and this is defined on the variable w. This is 1 by s square I, inverse of this. And then this is nothing but w transpose. So this is the quantity that you need to maximize now with respect to w. Yeah, any questions still here?
I make. I just had a small doubt above. How did you set mu2 to be 0? Was the, matlab, is that a different assumption from the ones that we made earlier for linear regression?
Yeah. So I kind of didn't write that. So this third one is correlation. There is no correlation between any dimensions. Fourth one is all of the diagonal entries are same, and fifth one is weights are centered around 0.
Right. Okay. Sorry.
And that's expectation of that.
Yep.
So yep. Now we are trying to optimize this with respect to w. Now this is log of c1 is just yeah. This would be log c1 plus log c2 plus log of exponent is this value. And now again, this is independent of w. This is independent of W. So now what we are interested is in again log C2 went out, log of exponential is just this value minus half W 1 by S square I. Yeah. So now since we can, this is a scalar quantity, this is a scalar quantity, this is just I, this is minus 1 by 2 sigma square y minus W transpose X. Oops. I think yeah, if you see here, it's a transpose first, and there is no transpose otherwise other. And this is kind of like important that you need to uh, be aware of where you show the transpose and where you don't, because now since I made this mistake, if I had it other way around, then this would be a n by n matrix. But the probab PDF is just a single value, and now if this is the real value and this is just a scalar. So sorry about this mistake. And then this is this transpose minus 1 by 2 S square W transpose W. Now this is same. So it's again X transpose X is mod of X square. We'll use this. Now what we are doing is y minus W transpose X. Now, I hope this is looking familiar to you now. And again, we can multiply, let's say we can multiply this by some constant. Again, minus half is the, yeah. We can remove this minus and do a minimization of this. Then multiply throughout by 2 sigma square since it's a positive. Then this goes away. This becomes 2 sigma square. Let's say I'm saying sigma square by S square is some positive value lambda. Now we arrive at this beautiful equation plus lambda W square. This is looking familiar to you. So this is nothing but just doing linear regression with regularization over the weights. And we, so as Kushal was saying, and I didn't want to ruin the surprise for you. So we are doing nothing different but just doing what regular machine learning does, and then just optimizing this. But all those assumptions that Chalisi was talking about and all of that, those come here in order to derive, in order to derive this from where we started. So yeah, and then this we'll come back to this, why we assume this probability distribution on W and what would have happened if we didn't. Like, let's say if we say we don't care about our weights are not uniformly distributed and our weights are just constant, and let's just optimize for this, then we would see that we wouldn't have gotten this term, and then we would so basically assuming a distribution on W and forces us to do some sort of regularization, which we do in machine learning. And if you remember, that's what we do, right? In machine learning, we say our weight should be small, and also it should be centered around zero. And this is what it's entailing. It should be centered around zero. And as you move far away from zero, this would the probability of it is decreasing. So this is enforcing that constraint that your weights are should be centered around zero and should be as close to zero as possible. And that's where basically we end up with this term, where this says that don't keep the magnitude of it to be high, otherwise, yeah, the probability of weights would decrease. And if we just discarded that, then and we allowed our weights to go anywhere, then we would this term would just go away, and then we would. So it's basically this second normal would just go away. in all of the cases, because we are not taking this log n2. This would go away, this would go away, and then we would just be left with this, and we would do a normal linear regression without any regularization. Yep. So I think that's it for the time that we have. And yeah, any questions? And yeah. Anything that was not clear, any mistake that I might have done, or any other questions?
Things that you'd like to repeat are also fine, like something that
Yeah.
there might have been a speed increase for and you want it to be slower. I don't know. Do you plan to have like a continuation next week or the week after?
Yeah. Yeah. So yeah. So like yeah. Of course, there is so much more to continue. Uh, yeah. So next week I'm planning to do likelihood and MEP and all of that.
Sounds good.
And then in order to solve this, you can just do an closed form solution of this or gradient descent or anything.
Okay. So like this is maybe a bit doubt, like I'm not sure. So here like basically we are basically we're breaking down the problem into two parts. Like so one is like finding out the actual optimum values and next is like restricting the weights like in a way such that they are more centered towards zero in a way, correct? So here if we kind of think of this as like in terms of Bayesian, yeah, like let's say, so then like the difference here in terms of Bayesian, it would be like it would be finding out like the distribution W for which this particular like the uh, sort of like the mean squared error is like basically smaller, like it's closer to the actual true distribution. But in this case, we are not restricting our hypothesis like parameter search to a particularly smaller like space in a way, or is it something different? Like sort of the relation between the two,
I
like.
didn't get exactly the question. So
So
can you repeat it?
I am saying is here in this case we have breakdown like there are two terms like correct first term and second term. First term is minimizing the squared error. Second term is like kind of a regularization parameter in a way. So if we think of this in terms of Bayesian machine learning here, so it would be sort of like without that regularization parameter, right? Or maybe it is sort of a bit different only anyway. Means like I think of that like a regression parameter as such just to restrict the hypothesis space, like so where we are searching the weights in a way.
No,
But otherwise, if sorry, yeah, go on.
it this term is simply like a sort of regularization that you want. So you are encoding your prior knowledge. It's like completely fine
No,
if you think
like
that you don't need W and you just discard it.
okay. No, like I am saying is that here we are like basically in terms of machine learning imposing sort of like for like some constraint based on whatever weight should be here. Like if we think of this in terms of Bayesian learning, Bayesian machine learning sort of thing, then you're like it would be sort of without that regularization term, but most of the other terms would be same sort of, right?
What
Or
do you mean by Bayesian learning as in like
as in like Bayesian machine learning, as in like matlab, in a way we are not restricting our search for like just one parameter or like within this sort of like a smaller space like in a way for the parameter, like we are basically trying to explore all the parameter like space that is available and like find out which parameters here are there. But in like machine learning way of thinking would be like just find out the parameters near to like the origin or like near to the center, like that maybe like so is it sort of like
you are not as in you are not restricting your search space. Your search space is like still the W can be anything, but you are penalizing it more if it's like away from the center.
but मतलब, that is in a way like restriction only na like मतलब के you are trying to restrict like मतलब के if you go more like away from the center you will be penalized more, so like that way like you are trying to restrict your like the area of like the
Yeah,
parameter searches, right?
yeah.
But
So,
again, if we don't have that particular, let's say L2 regulation that we have right now, so then can we like think of it as like sort of similar to Bayesian machine learning, or it is completely different in a way?
mm, it's if you like as I said, if you discard this, then you would end up here. And even this is like same as what we started out. It's just like instead of assuming normal, you are allowing it to be anywhere in the space. So it's like it's just simply a uniform distribution over one. This would
So
just be
मतलब
one. And now what you are saying is it's like it's not different from like even this is it's the same machine learning from a Bayesian perspective where we are assuming a distribution and using Bayes theorem to solve this. So I'm not aware how you are making the distinction between Bayesian learning and so this is same as like without the so and even by introducing W we are not losing anything. We are actually gaining something.
yeah. Like मतलब basically like a distinction that I made maybe like from like whatever we are discussing so far. So it's like in Bayesian learning we are trying to search all the possible like parameters like that we have like means all the hypothesis space that we have, and in machine learning we are just like searching over the small part of that hypothesis space like that we have. Correct? In some
Are you talking about this Bayesian inference that I said over all the possible values of theta? This thing.
yeah, but like मतलब based on that expression that we got now so far, like the minimization we have converted like the for linear regression problem.
Yeah.
So
So
if we let's say
the main
yeah.
difference where it came is where we kind of moved from doing a full Bayesian inference to doing it in the machine learning kind of way, where we discarded this denominator term, and we kind of instead of finding probability, instead of finding this, we went and started finding this. So I think this is where the main distinction between full Bayesian inference and doing it in kind of a machine learning kind of maximizing the likelihood sort of way, which we'll see later. This is where the main difference comes.
Okay.
Yep,
So
and
basically, we
yeah,
try to find a value of a W which maximize the this posterior, isn't it?
yep. So we are basically finding the mode of this distribution. We are discarding the distribution and just saying, okay, now we are just interested in finding the mode of this. So, yeah,
Right.
yeah.
So then at the end, when you wrote minimizing W, what that mean?
Yeah, so we are maximizing this quantity, and then since there was this minus sign and we needed to remove this minus sign, the maximization problem turned into minimization problem. So, now from maximizing this quantity, we removed this minus sign, then it became minimizing problem, and then we multiplied it with a constant positive value of 2 sigma square 2 s square, and then we got this.
All right. Okay.
To answer Deep's question, maybe it helps if you think about it as you raised a. I think you are going along the right track in the questioning. Um, and I've had this question too. So when you consider a frequentist versus a Bayesian perspective to the same problem, you're you can converge to the same solution in both cases. It is possible, and given enough data, you will converge to the same solution in both cases. Um, the challenge comes in when, for the frequentist way, you're basically doing a blind search, and you don't know anything before you see the data. Once you start seeing the data, you start creating updates that push you in different directions. In the Bayesian learning perspective, you're doing a guided search where you have some prior understanding of the problem at hand. You place some prior on your parameters, and this could be completely wrong. Like, you're not placing this with any knowledge of the data. You're placing this with the knowledge of your principled understanding, hoping that it works out. And so, like, there are just two ways to look at everything. One way is to say, each situation is different, and I can't use transferable knowledge from one situation to another, because I might be wrong, and that's not true. And the other way is saying, look, I know some things work in one way, other things work in a different way, and hopefully this will help me learn better. And so, in a technical way, when you're updating your posterior, it's a slower update than considering the frequentist way, where you're just jumping from one number to another. So when, in the simplest case for the coin flip, if you see one head, two head, three head, four head, five heads, your probability for head will go straight from 50% to 100%. there will be no intermediate point, right? Until you see a tail, that probability for heads will remain at 100%. Whereas in the Bayesian perspective, your probability for heads will go from 50 to 60 to 70 to 80 to 90 to 95 to 99, but it will not reach 100 because there will be some other probability distributed over the rest of the like probability values to confuse you. But probability of coin flip being heads will never be one. That's my point. No matter how much data you see, until you reach that infinite point where all I see are heads, and even then, like there will be some non-zero mass placed on probability of tails being more than zero. So that is the difference. That there are slower updates, but what you hope to gain is like this transferable knowledge actually working out for you. Whereas in the frequentist space, you're jumping from here to there to here to there, and you might end up being like reaching the same point in both, but here you're moving slightly slower, whereas there you're jumping around. Hopefully that helps.
Yeah.
All right, it was Jen or Deep.
Any more questions? And any other off track doubt that you might have? Any tangential doubt to any of the things that we discussed?
Also, like future questions, like questions you might have today might help him build a better lecture for the next week. So be sure to like let him know what you want to learn, and if he can, he will teach you. If he can't, obviously he can't, but it helps.
True.
Basically, I mean, what he went through today was the first week of Bayesian, the course, the Bayesian course. So it would be good if you like go through the remaining week of that.
Yeah. So that's the plan, kind of. So yeah.
Right. So are you planning to do like sometime in the between, like on the weekdays, or do you want to do like on Saturdays only? I'm saying because I'm doing the Bayesian course now, and if it's like if you do on the weekdays, it would be really good to follow with that rather than waiting for whole 1 week.
Uh, I, I I currently, I guess Saturday. If we want, we can increase the time on Saturdays. But yeah, I guess it would be better if for now, if it's just like because of the courses and everything that I have right now, I think it would be better if for now at least. But if we want, if we can, if you feel up for it, then we can maybe extend from 2 hours to 3 hours. That's completely fine for me.
Cool. Okay. Thank you.
All right, I'm gonna pause recording. Oh, stop.